This slideshow is about folds. Remember, rocks can be broken along faults or they can be folded. And this slideshow describes the different kinds of folds that you need to learn. Before we do that, you need to understand the different parts of a fold, and we have to have some kind of vocabulary to describe them. Here we have a folded layer of rock with the blue and gray. The plane that runs right down through the middle of the fold is called the axial plane. And the intersection of the axial plane and the fold itself is a line called the fold axis. In this particular case, the fold axis is horizontal, but as we'll see later, it doesn't always have to be. And a limb of the fold are simply the two sides of the fold that dip in opposite directions away from the fold axis. One of the simplest kinds of folds is an anticline. An anticline is simply a fold with a horizontal fold axis in which the beds dip away from the center. Here I've actually shown the fold axis dashed, which can see that it's horizontal, and I've shown some strike and dip symbols showing that the beds on opposite sides of the fold axis dip away from the center. Since in general rocks that are not badly disturbed get younger as you get closer to the surface, right? If you look at the distribution of rocks here, you can see that the anticline folding brings up rocks in the center that were normally buried deeper. So what it does is it brings up rocks in the middle that are the oldest rocks seen on the surface, and rocks get progressively younger as you move away from the center. Those are the characteristics of an anticline. The rocks in the center are oldest, and the rocks get progressively younger as you move away. Now notice that what's happened here is I've folded the rocks and then I've planed off the surface by erosion, and that is generally going to be the case. It's pretty unusual when you actually see surface topography which represents the folding of rocks. Rocks get folded, they get uplifted, and then typically they get eroded, and so what we normally see on the surface is merely the eroded plane that reveals the rocks that are folded. We don't actually see the folds themselves very often exposed as topographic features. Now, a syncline is sort of the opposite of an anticline. It's a simple fold with a horizontal fold axis, just like before, but now the rocks on opposite sides of the fold axis dip towards the center. And I've shown again the strike and dip symbols showing that's true, that the beds are dipping towards the center. Remembering that rocks get younger as we move upward, this means that in the case of a syncline, the youngest rocks are found in the center, and the rocks get progressively older as we move away from the center. These are the characteristics of a syncline. Now, so far I've been talking about folds in which the fold axis is horizontal, like shown here, but that doesn't always have to be the case. We can have rocks in which they're folded, and then the fold axis itself will be inclined to the horizontal. Those are called plunging folds. For example, in this case, we have a plunging anticline, a fold in which in this case, the fold axis plunges into the ground in the direction sort of into the screen. So a plunging fold is one in which the fold axis isn't horizontal, but dips or plunges into the ground. When we take an anticline and we make it a plunging anticline, what we find is that along the surface, the rocks, instead of being parallel bands, connect to form a U-shaped loop. So in this case, we have a plunging anticline. The plunge is always in the direction of the closed end of the loop. So in this case here, the rocks are plunging into the screen here, and so we can see there's the closed loop, and the rocks will plunge, or the fold axis itself will dip into the ground in the direction of the closed end of the loop. In other words, into the screen as shown here. That's a plunging anticline. On the surface, here's an example of what you see again on the surface. So the top diagram here is not a block diagram. It actually shows what you'd see on the surface of a geologic map, and we see these funny kinds of loops. If we know that the rocks are in an anticline, because we can tell which way they're dipping, we can see that in this case the anticline plunges to the left because that's in the direction of the closed end of the two loops for the two anticlines shown here. We can also have a syncline that plunges. When that happens, once again, we end up with sort of U-shaped distributions of rocks, but now the syncline fold, the axis of the syncline fold, plunges in the in the direction of the open end of the U, or open end of the loop. So if that's our little open end there, the syncline will plunge or dip in the direction in which the loop opens up. That's what a plunging syncline looks like. So once again, on the surface, what we actually have here is two anticlines separated by a syncline. And once again, what we see for the syncline is that the rocks are plunging always to the left here, and the axis of the syncline is plunging to the left too, and so it will be plunging in the direction in which that loop, the brown loop, opens up. Those are the characteristics of a plunging syncline. So here's a good way to test yourself here. Here's actually an air photo taken from a rather famous mountain in northwest Wyoming, sorry, called Sheep Mountain. And you should be able to see enough to actually tell what kind of fold this is. Can you tell? I'll give you a second to try to figure it out. Well, the first thing you might be able to notice is that this is incredibly well exposed, right? This hasn't been very well planed off. So we can actually see very clearly the direction in which these rocks are dipping. And you can tell, hopefully, that the rocks on both sides are dipping away from the axis or center of this fold, which runs right down the spine of that mountain in the middle. And therefore, that makes this an anticline, a fold in which the beds are dipping away from the center. However, we can also see the characteristic U-shaped distribution of those rocks, which tell us that this anticline is plunging. And remembering that the anticline plunges into the ground in the direction of the closed end of the loop, we know that this Sheep Mountain then is a plunging anticline that is plunging actually in a direction towards us. So Sheep Mountain is actually a plunging anticline. One other thing to remember about folds is that when rocks are folded, remember folding often takes place deep inside the earth, and so subsequent to the folding, the rocks have to be lifted to the surface if we want to look at them, and inevitably erosion modifies the surface. Very often then, the actual topography we see on the surface may have little to do with the way the rocks were folded. For example, here we look like we have sort of a valley, which at first blush you might think is a syncline, but that's actually not the case. What we have here actually is an anticline, okay? And what's happened is the anticline has brought up into the middle older rocks which are less resistant to weathering, and so they have eroded out more quickly than the surrounding rocks on the outside, producing a valley. That's actually a very common feature in many parts of the earth, where the valleys correspond to the cores of anticlines, because the cores of the anticlines are where we find the less resistant rock. Here are some other folds you should be able to identify at this point here. Here's a rather small fold. Hopefully you can see that's a syncline. Here's a much larger fold, a gigantic fold, and once again, this is a syncline. Here's another syncline with a truck for scale, just a gigantic syncline. And here is an even larger scale fold in the Swiss Alps, and this actually is an anticline. Hopefully by now you've got those anticlines and synclines down pat. There are two other structures you should know about, and they are called domes and basins. And they're actually very easy, and they're very similar to synclines and anticlines, or anticlines and synclines. A dome is nothing more than an anticline that plunges in all directions away from its center. So it looks like a set of bowls that are turned upside down. So as with all types of anticlines, in a dome we have the oldest rocks exposed in the middle, and the rocks everywhere are going to dip away from the center. Those are the characteristics of a dome. One of the best examples of a dome are the Black Hills of South Dakota. Now you're looking at this picture and you probably think that doesn't look like a dome at all, but this is kind of typical. Remember we said that the surface expression very often doesn't say much about the folds because that's all related to the erodibility of the different kinds of rocks. If we actually look at a geologic map of this area, you can see now that the dome structure is pretty apparent. The red rocks are the oldest rocks in this area. They actually consist of granitic rocks, the ones I showed you earlier. And as we go away, the purple and then the green and different various shades of green, those rocks are getting progressively younger. So this is the classic distribution of rocks found on the surface of a dome, with the oldest rocks in the center and rocks becoming progressively older. I'm sorry, I said it again. And rocks are becoming progressively younger as you move away from the center. Now, the opposite of a dome is a basin, and a basin just looks like a set of nested bowls sitting the way they normally sit, right? So a syncline is, I'm sorry, a basin is simply a syncline in which all of the rocks plunge toward the center in all directions. So just like a syncline, the youngest rocks are found in the center and all of the rocks dip toward the center. You can see the different strike and dip symbols shown in the various rock units on this slide. One of the best examples of a basin in the United States is found in lower Michigan. And if you were to drive around Michigan, you'd never ever know it because this is a classic example of a basin in which the surface has been planed pretty much flat. And so there's nothing really to see on the surface except there's no rock hardly exposed at all on the surface. We actually have to dig down to actually find rocks. And the only way you can really identify this as a basin is by identifying the different types of rocks and then using the fact that in a basin it's a circular pattern of rocks with the youngest rocks in the middle and the oldest rocks on the outside and rocks dipping towards the center. So if we look at a geologic map of the state of Michigan, this is what it looks like. Now you don't actually need to know what these symbols mean. Merely understand that the rocks in the middle, the ones that are pink, correspond to the youngest rocks in this area. And as you go away from the middle through the blue and then the purple and the green and the yellow and the gray, the rocks are getting progressively older. So this is the classic distribution of rocks in a basin. We have a sort of a bullseye pattern of rocks with the youngest in the center and the rocks getting progressively older as we move away. Further, if we were able to actually measure the strike and dip on these rocks, which in reality is kind of difficult because they're only exposed, most of them, in boreholes, but if we could measure the strike and dip, what we would find is that in every case the rocks would be dipping towards the center, towards where those pink rocks are found, the rocks that are actually Jurassic in age. That's what JUR stands for. So this again exemplifies a basin in which we have the youngest rocks in the middle, rocks getting progressively older as we go away, and in all cases rocks dip towards the center.